We'll now continue with section 3.3 and discuss 3 other types of common functions. We'll begin with the absolute value function, the graph of which is shown on the screen. This is the graph of the function y is equal to the absolute value of x. Note that for any value of x, the function is non-negative, so the graph will either lie on the x-axis or above it. Our first example asks us to sketch the graph of the function f of x is equal to -2 times the absolute value of x. When I compare my given function to the function that we looked at the graph of just a second ago, we see that the differences are we have a negative and we also have a 2. So we need to think about what effect the negative is going to have and what effect the 2 will have on the base graph. We know that the negative will reflect the graph over the x-axis. And the 2 will cause the graph to be vertically stretched. We've also discussed that it might be a good idea to determine several key points that you can use to check to be sure that you are graphing the graph correctly. For example, I might want to plug in a -4 and maybe a +2 for the x. And so if I do that, if I plug in a -4 into the function f of x is equal to -2 times the absolute value of x, the absolute value around the -4 would cause that to become positive. -2 times +4 would give me a -8. If I plug a 2 into the function, f of x is equal to -2 times the absolute value of x times the absolute value of 2. The absolute value of 2 remains 2. And -2 times +2 would be -4. And so that gives us 2 points that we can plot on the graph. So in order to graph, we can remember that our graph typically for our base function will look like this. And recall that we said the negative in our function will cause it to flip over the x-axis. And we also know that we have several points that we can look at. We have the point -4, -8, which is this point here. And we also said we had the point 2, -4. So over 2, down -4. And so knowing that the graph is reflected over the x-axis and crosses through those 2 points, that will enable us to sketch a graph of our function. Our next type of function that we'll look at is called the greatest integer function. The greatest integer function, f of x is equal to the x, and the x is in kind of a double set of brackets, is a function commonly encountered in computer science applications. It is defined as follows. The greatest integer of x is the largest integer less than or equal to x. So for example, if we had the number 4.3 inside the double brackets for greatest integer, then 4.3 would return 4. It gives us the largest integer that is less than or equal to the number inside the brackets. And so 4 is the largest integer that is less than or equal to 4.3. Another example would be to have a negative number. So what if we have the greatest integer function acting on -2.9? So we need the largest integer that is less than or equal to x. And so in this case, that would be -3. -3 is less than -2.9 because you're dealing with negative numbers. and it's the largest integer. It's the closest one to negative 2.9. When we graph the greatest integer function, we get a graph that looks like the picture on your screen. Recall that the open circles mean that that is not a defined value for the graph. So for example, if we have the greatest integer of 1, remember it's going to return the biggest integer that is less than or equal to the number we put in, and so that would be 1. And if we do in the greatest integer function 1.2, it's also going to return 1. 1 is the largest integer that is less than or equal to 1.2. If we put in 1.9, it's also going to return 1. 1 is the greatest integer that is less than or equal to 1.9. And so we can see those numbers. If we plot an x value of 1, the y value would be 1. That's the first point, it's right here. If we do 1.2 on the x-axis, we go up to 1. If we do 1.9, we go up to 1. But as soon as we go up to 2, the greatest integer function returns 2, and it jumps to the next step. Our final type of function is called a piecewise defined function. A piecewise defined function is a function defined by 2 or more formulas, each valid for a certain part of the real number line. In evaluating a piecewise defined function f at a certain value of x, it is important to correctly identify which of the 2 or more formulas is valid for that particular value. So let's try an example. Sketch the graph of the function f of x is equal to, and we have 2 rules. The first rule says negative 2x minus 2 if x is less than or equal to negative 1, and x squared if x is greater than or equal or greater than negative 1. And so let's consider our solution. What I'm going to do is I'm going to take each of these functions and I'm going to graph each one separately. So I'm going to graph negative 2x minus 2, and I'm also going to graph x squared. So in order to graph negative 2x minus 2, I may want to do a couple of points. I know that that's going to be a linear graph. It's going to graph a line. I just need to know where to put it. So if I plug in 0 and evaluate f of 0, I'm going to have negative 2 times 0 minus 2. The negative 2 times 0 will fall out, leaving me negative 2 for an answer. And let's try one other value. Let's try negative 1 for the x. If I plug in negative 1 for the x, we're going to have negative 2 times negative 1 minus 2. Negative 2 times negative 1 is positive 2. Minus 2 is going to give me 0. All right, so now I have 2 points. I can do a very quick sketch of what this graph is going to look like. I'm going to plot the point 0, negative 2. Which will be here, and I'm going to plot the point negative 1, 0, which will be here. And I'm going to connect those lines, or connect those dots, making a line. Now I'm also going to go ahead and graph the function x squared. And we know that that is our basic parabola centered at the origin. If you're not sure about that, then you can always come up with a couple of values there as well. But I'm going to go ahead and sketch that in. Now, the other thing that I need to consider is that these graphs are only apply in certain situations. So the first graph is only good when x is less than or equal to -1. And so what I'm going to do is I'm going to find the -1 on the x-axis, and I'm going to just sort of separate this graph with the dotted line for a second. Here's the -1 on the x-axis. And this graph is only going to apply for x values that are less than or equal to that. So that's going to be only the left side of the graph. And so I'm going to come in here with my eraser, and I am going to erase the right side of the graph. So everything to the left of that dotted line is going to stay, and everything to the right will go away. Now we'll do the same thing on the other one. The other one is good for x values that are greater than -1. So again, I'm going to dot in a line at -1. And we're going to keep the part of the graph where the x's are bigger than that. That would be the right-hand side. And we're going to erase the left-hand side. And we should notice that this does not have the equal sign underneath it. So that means at -1 we have this open circle. Because this does have the equal sign at -1 on the first graph, we have a solid circle. And so what we're going to do now, and you'll see this when I flip to the next slide, is we're basically going to take these two graphs, which is a left-hand part and a right-hand part, and we're going to slide them together and make one graph out of it. All right, and when we do that, you can see that our graph looks something like this. All right, so this is the left-hand part that we already had. This is the right-hand part that we had with the open circle. They've now been merged into one graph.